This is FE Peer Review. The date is March the 30th, 2025. Data and analysis to complement Bobby Shafto's recent long-distance observations. Bobby Shafto has recently moved up to the Pacific Northwest, and he's found a spot near Seattle where he's been able to make some very interesting observations of ships coming and going through this one area of the waterways there. It's called Commencement Bay. And he's got a bunch of videos he's started. I look forward to seeing more, and he's doing some interesting observations and analysis. I wanted to add some of my own analysis to it. He had requested people to contribute, so that's what I'm doing here. I've put a link to his channel in the description, so do head on over there if you're curious to know more about it. Here we have a little view on Google Earth of the area we're talking about. Seattle-Tacoma Airport's up at the top center. There's a port down here at the bottom, Tacoma. And he has set himself up at Dinkman Mill, doing an observation across the water. Two land masses, Browns Point and Point Robinson, provide some very useful reference points. And then he can see the distant shore near Seattle. So that's the area that he's going to be observing regularly, and that's the area we're going to look at briefly in this video. Here's a screenshot from one of his videos. We can see Browns Point Lighthouse on the right, Point Robinson on the left, this small house, white house here where I'm circling the mouse, and then the distant shore. There's a house right down near the water on the distant shore, and as you can see, there's a ship coming in at the time he's doing this video. He's got several of these with different ships coming and going, but I'm just going to look at this one. He has identified that his observation height is 17 feet above the water. At the time he did this video, he measured it to the actual water line. He wasn't using mean sea level or anything like that. So his observation is 17 feet above the water at the time this video was taken. And he asked people to identify on the various objects in the photo, where would 17 feet up from the water be? So on the lighthouse on Browns Point on the right, how high up do you have to go to reach 17 feet? The same for Point Robinson, the house on the left, the distant house by the water, and also on the ship. So that's what I'm doing in this video. I'm identifying the 17-foot high mark on each of these structures. Let's start with the closest one, Browns Point Lighthouse. I took a snippet from that image we were looking at before and enlarged it as much as I can. And then I thought maybe I can find something better or more useful than this for actually trying to determine some dimensions and establishing the 17-foot point. I did end up finding a very nice clear shot of the lighthouse taken from not too far away and pretty much straight on. So we're getting a pretty much undistorted view of the lighthouse here, one that we can measure off of reasonably well. We're not trying to measure down to the fraction of an inch. A couple of inches this way or that's not going to affect our results. So I wanted to find out some information about the lighthouse. In particular, I needed to get some data about its dimensions, and that was a bit difficult. There don't seem to be any good online resources with drawings of the original construction or anything like that. But I did find one resource here, a regional history website. It said that though in 1933, the wooden lighthouse on Browns Point was replaced with a 9.5-foot square Art Deco style concrete tower, 38 feet high. Now I found some other references to the height of the structure at 30 and 34 feet. And I also found a reference that said 38 feet high, which was sounding as if they were referring from the center of the light to the water line. So I think that these 30 and 34-foot figures represented different aspects of the building, like the height of the tower with its base and its light and so forth. So it was a little difficult I wasn't confident with the height figures I was getting because they were a little bit ambiguous. However, that 9.5-foot square dimension, that I thought was really useful. So I worked based on that. I took this image here and I put it in Photoshop and I created what I'm going to call a ruler. Basically If you go across the top here, you'll see red tick marks. I'm going to zoom in. So you see the red marks that I made. And if you count across, starting from the left, we have 9 and 10. So this corner falls at about 9.5 feet. And based on that, I could have a reliable 10-foot long ruler that I could use to then measure the height of the lighthouse. And for that, I started with the top one, the top end of my ruler up at the light. And then I just worked my way down. And I got, for the height of the main block of the tower, so from the base here to the top here, the main block of the tower, I got 25 feet, which was a nice, easy number to work with. So that's what I used. If you look on the right here, you can see the lighthouse, and I'm going to zoom in a little bit. I took the main block of the tower and I established that as 25 feet. Then, simply counting pixels, I created a second ruler that was 17 feet based on the same number of pixels there. I made a ruler that was 17 feet. I placed the bottom edge of that ruler at the water line and then measured up, and that gave me from the water the point on the lighthouse that's 17 feet above the water line. So that's how I decided where the 17-foot mark would be relative to the water line. And I placed that on our base image here. I'm going to repeat that process for the house on the left, Point Robinson. The house at Point Robinson poses a few other different kinds of problems. There isn't any documentation that can provide strong values for the dimensions of the house. And you can only get so much from Google Earth Street View. The Street View automobile doesn't actually go into the area, but they have a few still photos that they've got on Google Earth. So we're looking at one of those now, and this one is fairly useful. The house itself, that's this structure back here. We're looking from the other direction at the moment. The house is built on a sort of level terraced area, and then there's a little bit of a drop, a few feet of drop, and then a beach that goes down to the water. This is the image from Google Earth. This is not from Bobby Shafto. So the water line, it was taken at a different time, and the water line, it could be a very different point in the tide. I don't know whether this is low or high tide, but it looks to me like it's fairly low because we see that there's algae up here, and we see that there are even logs further up the beach. So the water's often up in this area. So I'm guessing this is a fairly low tide, and it might be reasonably close to what Bobby was working with. We've got the horizon here, and we've got our photographer standing pretty much right near the water, within inches of the water's surface. As he looks over in this direction, we see another fellow standing over here. He's back a little ways from the water, but his head is approximately eye level in line with the horizon. So if the photographer's head or the photographer's camera and this guy's head are probably at the same elevation within a few inches. This annoying sloped horizon here, so I'm going to go over to Photoshop. I've put those images in Photoshop and I rotated it so that we're looking at something that's straight. So there was the image I copied from Google Earth. And here I've rotated it a little bit to flatten out that horizon there, make a straight line across. And we see that that line passes through the eye level of the other fella. Up here on the right, there's another woman. There's a woman standing here who is up higher, and we can see that her head is above the level of the photographer and of this fellow. And our red line passes a little bit below the level of the terrace. So I think looking at the water line, the eye level of the guy standing here, the eye level of the woman standing here, I'm estimating that it's about 6 feet from the water to the eye level of this guy, and then another foot or so to the terrace, and then another foot or so to the woman in the distance, her head. So I'm going to call this terrace 7 feet above the water line. And I'm going to assume since we can't get any data on this, since there's no way to get any data on this, I'm going to assume that this water surface is near what Bobby Shafto was seeing. Here's the enlarged image from Bobby's video. Got the house here. We can see some of the beach with some of the debris and all here. And then this dark object, that is a picnic table, dark picnic table on this terraced area. And then we have the house. We're going to look now at the house in more detail. There are two photos on Google Earth that we can use. This one is very useful, although we've got this annoying fence post in the way here, but we can work around that. I'm going to fall back on some of my architectural knowledge here. We're in the Pacific Northwest, where wood is the most common building material. The siding is called clapboard siding, and typically clapboard siding comes in 4-inch, 5-inch, and 7-inch dimension, and that's called the exposure, and that's the distance from one board to the next, the amount of wood that's exposed to the weather. They overlap, so the boards themselves are a little wider. I looked at this and thought, okay, it doesn't look like 7-inch exposure. It's either 4-inch or 5-inch. I counted the clapboards for this window. There were 6. At 4 inches, that would be 24 inches high for the window. At 5 inches, that would be 30 inches high for the window. This window, to me, proportionally does not look like it's 2 feet high, 24 inches. I would say it's more likely 30 inches high, and that would work with the 5-inch siding. So I came to the conclusion based on that the exposure on these clapboards is 5-inch. And although we've lost the bottom one here behind the rail of the fence, if we count that, we end up with from the floor to the top of the wall here, we end up with 12 feet high, which really jives with what I would expect for a house like this. They would typically build the wall from the floor to the eave in one piece. So in this case, a 12-foot wall. The ground floor, the lower floor, would have an 8-foot ceiling. Then there'd be floor framing. And then the attic level would have a knee wall. They call this a 1.5-story house, where the half story is the attic, which has rooms in it, habitable rooms in it, usually the bedrooms. So based on what I measured with the clapboards and what I know about house construction in this type of house, I'm estimating that this wall height from the floor line to the eave is 12 feet. If we go to this image, we can see this is the corner we were just looking at, and this is the window I was talking about. We can see that this line right here is the floor line. Below that, there's a band, which is floor framing, and then below that is the foundation wall. This house is built on a partial basement, so the basement is about 4 or 5 feet deep, and then it extends up above the ground about 3 or 4 feet. Then they built on top of that. I know that there have been floods in this area, and the water has come up to the ground level here at times. I saw some photos of that. So they probably built it up 3 or 4 feet above the ground in order that any flooding that might happen would only be in the basement and not in the living area of the house itself. So based on this wall being 12 feet high, I measured that counted the pixels, and determined that we've got about 4 feet from the floor line down to the ground. It's hard to say because it varies. The ground is sloped a little bit and varies as you go around the house. But at this corner here, it appears to be about 4 feet between the floor line and the base of the wall where it meets the ground. So I created a little ruler here, and it gives us 16 feet from the eave to the ground. Taking that information, I can go over to the house now on the main photo here, Bobby's reference photo. I'm going to zoom in a little bit. We had 16 feet from the eave to the ground of the terrace. I made a second ruler over here that's slightly larger at 17 feet, and I placed that at the point where I saw the ground and the water meeting and brought that up. Now, if there's obstruction happening at that shoreline, and there probably is a little bit, 1 or 2 feet. If there's actually curvature obstruction happening, the bottom of my 17-foot ruler ought to be a little bit below the water line. But I'm just going to go ahead and place it at the water line for now and set it at 17 feet. And then on that basis, I'm going to estimate where on the wall here, our 17-foot mark is. And basically it's this red line here. So that'll give us our reference point on the house for our 17-foot elevation above the water line. The next thing we're going to look at is the boat here, and we've got another view of it that's very helpful. Further into Bobby's video, the boat goes past very close up, and it's got these letters tote written on the side. I decided to use as a reference dimension the haploid container that's up on top. I went to their website, and unfortunately it wasn't really all that helpful. They didn't actually have the dimensions of the exterior of the container. They had the interior dimensions of the container, but they did have this little bit of text down here, the ISO type group, which just basically says what kind of a container is it? Is it ventilated? Is it refrigerated? And so forth, which is not relevant to us. And the ISO size type, which is exactly what we need. It's 22G1. So I looked up the ISO, that's the International Standards Organization. I looked up the ISO codes and what they are. And I found a website from German Insurance Association. This is an organization of insurance companies that insure shipping. And on their website, they had the ISO codes listed. So what it tells us is 22 tells us that the height of the length is a code 2. And for a code 2, that's a 20-foot length container. And then the height is also a code 2. And if we look at down here, code 2 is an 8-foot 6-inch high container, and that's the exterior dimension. G stands for general. So it's just saying it's not some kind of special like refrigerated container or ventilated container. So we know our container is 8.5 feet high, 8 foot 6 inches high. And that was exactly the information we needed. So using that information, I created a ruler, an 8.5 foot ruler, which is right here. And then I counted pixels and created next to it a 10-foot ruler. And I extended that 10-foot ruler all the way down the side of the boat to the water line, but to pass the water line. So we have 10, 20, 30, 40, 50, 60, going all the way down. And that was useful in a couple of ways. For a start, it gave us a height on the letters. If you count the tick marks here, I'll zoom in a little bit for those who want to. If you count the tick marks, it's between 19 and 20, close to 20 feet. So these letters, I'm just going to call them 20 feet high. And then again, if you count the tick mark from the bottom of the letter to the water line, it comes out to like between 16 and 17 feet. From the water line to the bottom of the letters is almost our 17-foot mark that we're looking for. Our 17-foot mark is going to be just slightly above the bottom of the letters. So now we've got all we need to put that information into our reference image. We'll have a 17-foot mark for the Brown Lighthouse, another for Point Robinson, and finally we can see that the distance from the bottom of the letters to the water line is quite small here. At this point, the ship is beyond the curve. I pointed that out in an earlier video where I pointed out that you cannot see the wake the boat is creating as it's passing through here. So I'm going to annotate this image now with the 17-foot marks on the 2 points, and I'm going to put that 17-foot mark on the boat and show where that would leave the actual water line. I've transferred those 20 and 17-foot marks that we just saw onto the reference image here. You can see the 20-foot of the letters and the 17-foot below. The water line at the boat was between 16 and 17 feet. I didn't worry about the 4 to 6 inches there. I'm going to go back to Google Earth for a moment just to kind of recap. We are down here at Dinkman Mill. Bobby Shafto's down here at Dinkman Mill. This camera is 17 feet above the water line. Brown's Point, that square lighthouse, is here on the right side of the image. Robinson is on the left side of the image. That's the other house. And then that ship has just passed behind Robinson and is coming along this side here. Now at the far shore, there's another house near the water line. That's what we see right here in the image. You'll note that it has a, let me zoom in a little bit, and you'll see that it has a kind of simple sloped roof shape, and then there's a wall below that. We're going to take a look at that house more closely and try to estimate where the 17 feet above the water line would be on that house. So here we are looking at the house. Unfortunately, Street View doesn't go in there. So this is the roof line I was describing, the larger block on the right and the smaller block on the left, and that's the wall that we were seeing. Looks to be a wooden wall. What I want to point out, though, is now we need to make our way down to the shore, and what I'm seeing is a couple of things. First of all, there's a driveway up here, comes down. There's a driveway that slopes all the way down and eventually all the way to the beach. Right in here, we can see that this house is actually built up on a basement level, and it has a garage door here. Now, they've got something blocking it. They're probably not actually using it as a garage anymore. That's probably their garage. But this door is large enough to be a small garage door. So I'm estimating that door is probably about 7 feet high, which would make the wall 8 or 9 feet high, which is about right for a normal sized house. And then we've got the roof on top of that. So starting at the eave and going down, we've got about 8 or 9 feet here. And then another 7 or so gets you to the bottom of this garage door. Let me zoom and adjust the view a little bit. We can actually see a couple of minivans parked over here. And then it continues to slope down. We see this retaining wall here, and we see retaining wall along here, and then a bit of beach. So I'm going to just kind of put some numbers out there and see where we end up. Let's start at the eave here and try to work our way down. Going down about 8 feet for the wall, and then another 7 for the basement level. This ground here is probably about equal with the basement because they were probably able to drive in and out of that garage at one point. So that makes 8 and 7, that's 15. And then it would continue to slope down. We see there's about a 3-foot drop here at the terrace, and perhaps another 3 to 5 feet here. That would be 8 feet. I'll err on the conservative side and call it 6 feet. So we were down 15, probably down another 6 feet gets you to the beach, and then another foot from there. So that's 8 and 7, 15, 20, 22, so maybe 22 feet, probably between 22 and 24 feet down from the eave to the water line. So now let's work our way back. If that's say 22 feet, 17 feet would be down 7 feet from the eave line. So near the bottom of the wooden wall here. A little bit above the bottom of the wooden wall would be our 17-foot line. Starting at the beach, working our way up the basement wall, and then another foot or two up the main level wall. That gets us our 17 feet. I don't see that there's any way to be more precise than this, given the data we have. So back to our reference image, the 17-foot mark will be just a little bit above the base of that wooden wall. So about 6 feet below the eave of the house. Well, that's all we see. We don't see anything of the basement. We don't see the driveways or the beach. None of that's visible. So I'm going to put that reference line right at that 17-foot mark, right at the water line. That seems to be about where the bottom of that wall is. So from there, to get to the water line, we'd need to go down another 17 feet. And can we figure out a ruler for that? If we say that wall, that wooden wall, this portion here is 8 feet, and mind you, it could be 9 feet, it could be a foot more, but I've just been saying 8 because that's the conservative assumption to make. If that there is 8 feet, And if we're seeing 8 feet, and if we're seeing all of it here, then that gives us something we can use as a ruler to establish the 17-foot distance. So I'll do that next. Okay, I measured off the 8 feet best as I could. We're down to very few pixels here. And then from that, I went down 17 feet because it's like that wall is pretty much along the water line. That gives me 17 feet, all of which is below, obstructed by water. But that gives us what we need. Now, you may recall on Bobby's original video, there was a gentleman by the name of B Flat who left some comments, apparently a flat earther, seemingly a flat earther. In the course of his comments, he mentioned something that I just want to bring up because may be the case. I really can't quite tell. He was saying that in his opinion, we're seeing some mirage happening near the waterline. Basically, I gather from the way he described it, basically this zone right here, horizontally across the image, may be having some mirage, and what we may be seeing is obstruction of objects by the mirage rather than by the water surface, by the curved surface of the water itself. And I think he may be correct that there's a bit of mirage in there. I will turn those off for a moment. For example, we see here a dark rectangle, and that would be a window on the house. And we see another dark rectangle here. There is no second window on that side of the house. This is above the garage door. There is only one window. So this may be the reflection in the mirage of this window above. And we see that there's a little bit of stuff happening along here, sort of horizontal band along here. So yeah, there may be a bit of mirage in there, which may be responsible for covering some of these things. Now, I don't think it's possible to argue that the mirage is covering very much, because I want to point out that if it was a deeper band than that, the ship, which is closer to us than that distant house, we don't see any reflection of the letters. And if the mirage band was happening in front of the ship as well, and if it was a deep band, some of the lettering, at least some of the lettering, would also be mirrored, reflected downward, as we saw there was a bit of that by the house over there. So I just want to mention that point. It could be that there's a bit of mirage happening on that distant house, so this kind of complicates using so few pixels as a scale, especially when they've been miraged a little bit. That said, that mirage definitely, let me turn those back on. That we were talking about this narrow band right here on either side of this middle red line. This band right here. There's no hint, I can see no hint of that extending as far down as where I think the water line must be for that house. And there's no hint of it being over here with the ship either. So I just wanted to touch on that because B Flat had brought it up, and I do believe that there was something to his critique, but not enough to nullify what we're seeing. All right, we started this exercise with a specific task, and it took us a little roundabout path to get there, but we're there. Bobby asked us to establish a mark at 17 feet above the waterline on each of these 4 objects. And now we can do that. I'm going to start with Point Brown Lighthouse on the right, which is the closest. And I'm going to draw a line across part of the image here so that we can compare it nicely to the other lines we're about to draw. So that's 17 feet. If we were to extend the lighthouse mark all the way across the image, we see that 17 feet up from the Point Brown Lighthouse. Now 17 feet up the side of the ship here, right here, that's also 17 feet. And then our Point Robinson house, it was this tick mark down here, this one right here. And finally, the distant house, which is a bit problematic because of the possibility of a bit of mirage and there being so few pixels to work with. So there you go. It looks like the house, Point Robinson, and the ship are pretty nearly the same distance aligned, and so the same distance from us. Point Robinson on the right is closest object to us, and the house on the shore opposite is the furthest, and we see that the 17-foot marks drop as we get further and further away from us. What does that mean? Well, we're going to take a look at a quick diagram I put together in SketchUp's companion program called Layout. This diagram is totally illustrative. It's not to scale. It's just in order to explain a basic concept. Let's take a look at the upper piece here. We've got Bobby's position over on the left here, and his point is 17 feet above the water line. Here's the water line, this thick black line here. He's looking off to the right. And no, this is not perspective. This is just to illustrate a concept. If the surface that we've measured our 17 feet from is flat, level, horizontal, all of those things, then that's going to be 17 feet all the way across. That line of sight is going to be 17 feet above this surface here. At the far shore, we've got another house that's raised up a certain amount above that water line. And partway along, we've got another house, that's the Point Robinson house, also raised up a bit above the water on its own little terrace. Now, if we've established that, say, this point on this house at Point Robinson is 17 feet above the water, and if we've established that this point on this house on the far shore is 17 feet above the water, then when Bobby looks in their direction, they should line up. That point should line up with that point. If the surface he's on is a flat, level, horizontal surface. But that's not what we see. No, what we see is that the 17-foot mark, which is this green line off to the left here, at the Point Robinson house, is not aligned with the 17-foot mark of the distant house. What might be the cause of that? Well, what happens when that surface is not flat, but actually curved? Now, I've grossly exaggerated the curvature here, but if it were a curved surface, and then we establish, okay, take Point Robinson house. This point on the Point Robinson house is 17 feet above that curved surface, just like it is here. And this point on the distant shore house is 17 feet above this surface, just as it is here. But as Bobby looks out at them, he looks at the 17-foot mark on the closer house, and then he looks at the 17-foot mark on the more distant house. That would be the red line. And we see that that red line is below the green line. So even though they're both 17 feet above the water, one of them appears below the other when seen from Bobby's vantage point. And that's precisely what we see in Bobby's photo. So I have not taken into account things like refraction. I haven't brought up refraction in any of this discussion. Refraction, as it's understood by the vast majority of people involved in the subject, tends to raise the apparent position of distant objects. So refraction would actually work against our position here, and we're seeing something it would assist us in making things look flatter than they actually are. This is a problem for flat Earth because what the flat earthers need is something that makes things that are far away look lower than they actually are, which is the reverse of what refraction does. Now, I'm not going to get into all about refraction in this video. I've got other videos on that subject. I'm going to put a link to one of them in the description. Let's just say that in this case, it's only going to hurt the flat Earth position if we talk about refraction here, because they need to prove that their reverse refraction is true in the face of a huge amount of science that says otherwise, which I mentioned in that other video. So that said, I think we find that Bobby's photo, when analyzed as I did, aligns much more closely with the globe model than it does with the flat Earth model. Now, I doubt very many of you are going to be surprised about that. The one or two flat earthers that might actually see this probably will disagree. They're welcome to provide detailed information in their comments that supports their position, or to refer me to other videos. If you have a video that you think does a good job of supporting your case, mention the channel name and the title of the video in your comment. I recommend against putting a link, because YouTube often blocks comments with links. If you put the title and the channel name, I will track it down and I'll put the link myself. And that way you'll be sure your comment doesn't get blocked. Anyway, that's today's little game. I hope you found it interesting. I think Bobby should find this useful. I hope so. I'll probably do another one of these along these lines in the next few weeks as he produces more of his observations. If you enjoyed watching this, do click the like button if you haven't already subscribed. New subscribers are always welcome. And most of all, leave a comment. I love to read you guys' comments. They're always interesting. Have a great day. Bye-bye.